See, today we'll mainly emphasize on POC related questions and what are the important areas. Other than that, salt analysis. Okay, so let's see there. First, when it comes to separation techniques, what you really need to know is about the terms like sublimation, and I'm sure you know the process, but mainly to do with the examples and any principle that is underlying that. Okay. Here the principle is very simple, that anything which is sublimable volatile compounds, right? Those are the ones which can be separated or which can be purified. So purification of compounds like camphor, naphthalene, camphor, naphthalene, anthracene, benzoic acid. Benzoic acid is like a white color powder, okay, which can be sublimated. Then we have phthalic anhydride, phthalic anhydride, anthraquinone, okay, iodine HgCl2, sorry, iodine and HgCl2, and we have solid SO3. These are typical examples of sublimation. Okay, keep that in mind. Next, crystallization. When it comes to crystallization, here the principle is where the impure compound dissolves in solvent is sparingly soluble at low temperature, but it is highly soluble in at high temperature. So impurities will dissolve more easily. Correct. So remember the principle here. The principle here is impure, right? Impure compounds, okay, are low soluble at low temperature and high soluble, high soluble at high temperature. So that's the difference here we need to figure out. Okay. Based on that, what are the examples? Got it? Which would be used in here. Correct. See, first we need to understand what are the solvents for crystallization. Correct? Because we require to make those substances to dissolve in this solvent. After that, we need to crystallize the desired compound. Okay. Solvents which are used for crystallization includes water, alcohol, okay, ethers, chloroform, correct, CS2, acetone, benzene, petrol, okay, or petroleum ether. These are typical solvents which are used for making crystallization. Either it is crystallization or fractional crystallization. The idea is very similar, correct? So, in case if you want to crystallize the substances out, then this is better useful, correct? And sugars generally can be crystallized from here, correct? And using ethanol is one way, okay? While mixture of KClO3 and KCl are used, that can be separated out. Okay. Examples here: sugar, which is an impurity in common salt. Sugar is in salt, impurity in salt, can be crystallized, can be crystallized by hot ethanol. Correct? Another example is KClO3 and KCl can be separated. Okay, out of that, this is more soluble form. Okay, so we can add it to water and we can separate these two based on crystallization. Next one is distillation. Next one is distillation. Distillation has many techniques. One is simple distillation. First one being simple distillation. See, the idea here it should be very simple that there should be temperature difference greater than or equal to 40 degrees centigrade. Correct? Then simple distillation is used. Acha, in JEE mains question, they sometimes use 30 degrees or, even for that matter, 25 degrees also be used. Clear? Got it? So then we can say simple distillation can be observed other if the option does not have fractional distillation. Keep that in. Okay? Got it? But if the option is given fractional distillation and the temperature difference is less than 20, less than 30, then you go for fractional distillation in that case. Correct? So here examples, what you need to learn, mainly focus on examples. Chloroform plus aniline. Chloroform plus aniline. These two can be separated out using simple distillation. Okay. Ethers, ether plus toluene. Simple ethers. These are simple ethers, what I'm talking about. Then benzene, clear, plus aniline. These two can also be separated out. Their boiling point is quite the difference. The difference is high. Next one is fractional distillation. Fractional distillation. In here, delta T has to be less than 40 degrees. Got it? It has to be less than 40 degrees. Like I said, again 20 degrees is given, 30 degrees is given, you still go for fractional distillation only. Got it? So, examples in this case where we can use is acetone plus methyl alcohol, correct? And we can have benzene plus toluene. These two can be separated out by this case. Clear? Right. Next, if you have methyl alcohol, CH3OH, and ethyl alcohol, these two can be separated out by fractional distillation as well. So if you find these kind which are very similar, right, in structural features or in their dipole moments, then you go for fractional distillation. Next one, distillation, distillation under reduced pressure, distillation under reduced pressure, which is also called as vacuum distillation, vacuum distillation. Got it? Again, I'm sure you know that these are to be done for those compounds where the boiling point is very high. Okay. And examples where if the boiling point is very high, let me put down that here. If the boiling point is very high and it decomposes as you reach this time, decomposes, okay, decomposes around boiling point. So to stop that from decomposition, we use reduced distillation or vacuum distillation. Glycerin is the best example or anything which are of a similar kind. Glycerin, peroxide, formaldehyde, got it? And glycerol, right? So these are the ones which can be utilized. Next, steam distillation. Steam distillation. Steam distillation fundamentally is one compound, the separating compound must be steam volatile. Use this, see these words in the options, okay? It should be steam volatile, correct? And it should be insoluble in water at normal temperatures. At room temperature, it should be insoluble. Clear? Right. And impurities must be non-volatile. If these conditions are met, then steam volatility or steam distillation can be done. Okay. Lot of examples here, guys. Aniline, if you have to separate aniline from other sand-like impurities, correct? Nitrobenzene, we can use this nitrobenzene, bromobenzene, bromobenzene, orthonitrophenol, OH and NO2, and orthohydroxybenzaldehyde or salicylic acid, OH like this. Okay, ortho hydroxy acetophenone, right? So we have OH here and double bond O CH3. This one, turpentine oil, turpentine oil, and essential oils. Okay, anything of these kind, if you notice, they all can be separated out using this one. Okay. Yeah. Next, solvent extraction. Solvent extraction. If you notice solvent extraction, which is also called differential extraction, uh, it is used when solvent should be immiscible in water and organic compound should be able to separate them, in which this solvent is highly soluble. Got it? So in a simple way, impurities will should get dissolved in water and organic substances should get dissolved in organic layer. Got it? So we will have two layers here, organic layer and aqueous layer. Correct? So suppose if you have benzoic acid, benzoic acid, okay, extracted in extracted in benzene as solvent, benzene as solvent. Yeah. And generally, if you have any mild polarity also for compounds with mild polarity, mild polarity, ether is the best solvent, is the best solvent, correct? So that's why this was a question in 2024 also, which is the best solvent in differential extraction. That's how it is being asked. It is ether. And reasons for ether also were asked because of less polarity. Ethers have less polarity, less reactivity. It's not like they will react with that organic compound added. It will have relatively less boiling point and higher solubility, higher solubility of organic compounds. Now, unfortunately, you may have to also choose best out of these four, best out of these four options, like less polarity, less reactivity, less boiling point, and high solubility. Out of this, if the question is framed like this, that in differential extraction, which is the important property, then please remember this last one is an important property. Higher solubility is the most important property. Got it? I suppose this logic is clear. Next. The next technique for separation is chromatography. Chromatography. Okay. Chromatography mainly has two important parts of it, because when you want to separate a mixture, correct, it is separated based on two phases. One is called stationary phase, clear? The other one is mobile phase, correct? So just remember that stationary phase, this could be a solid or liquid, clear? Right. While when it comes to mobile phase, right? So this could be liquid or gas. Could be a liquid or a gas. Clear? Next, see, if a substance is being separated, using a solvent, this process is called elution, and the solvent used is eluent. So eluent is more related to mobile phase, and eluation is a technique to separate that molecules. So just keep this in mind. Next, as per the syllabus, you have mainly two types of adsorption, two types of chromatography. One is adsorption chromatography, and the other one is partition chromatography. Partition chromatography. Okay. Now, adsorption chromatography, here we will have mainly stationary phase and a mobile phase here. So I'll write it as stationary phase and mobile phase. Here also we will have stationary phase and a mobile phase. Correct? So typically, if you have a solid here, and a liquid here, here, this type is the most common one, which we call it as column chromatography. This is called column chromatography. Got it? Next one, which you need to understand, is this could be liquid or solid, right? While this is only liquid, then this is called thin layer chromatography. TLC, thin layer chromatography. Got it? Next, when it comes to phases here, where we have liquid and liquid, clear? Liquid and liquid. In a partition chromatography, if it is liquid and liquid, then it is simply called liquid partition chromatography. Liquid partition chromatography. Got it? Next, in case if you have something like a paper chromatography, where we have either uh, this part is a liquid here, here, and this passes either gas or liquid, this could be a paper chromatography. Mainly you are supposed to emphasize on these four types of chromatographies. Got it? And since in adsorption chromatography, majority of the time we will be using solids. Liquid is a very rare case, but it is always about solids. The types of solids which we'll be using here is silica gel, Al2O3 or gamma Al2O3, magnesium oxide, okay, cellulose powder, cellulose powder, activated charcoal. These are the materials used, okay? So just keep that in mind. Whenever we are talking about adsorption chromatography, these are the materials which we will be using, okay? Now, there are many questions that have been framed in here, especially when it comes to chromatography. Like, what are the, I would say, uh, compounds which can be separated, and while separating out, which will come fast, which will come slow, like that. Okay. So it all depends upon which type of solvent you are using. Majority of these solvents in adsorption chromatography are generally polar polar phases. Here these are mostly polar phases. Therefore, they attract polar molecules and make them spend make them spend more time in column. So if more time is spent in the column, that means it must be polar. It must be more polar. Correct? So questions of these kind would be asked. So just be careful with that. Right? So what exactly are we checking out? Next. I have noticed mostly questions related to thin layer chromatography. Here again, the in thin layer chromatography, the solvent which we are using, correct? I mean the stationary phase which we are using here in thin layer is most of the time silica gel. This is silica gel which we are using, correct? And there will be a plate which is being used, a plate which is being used here, correct? Which is of zero point 0.2 mm, clear? 0.2 mm thick, right? And sorry, 0.2 mm thick, and where it will be above is 2 centimeters above where the spot is been mentioned. The spot will have the mixture, correct? So as the spot moves, this is called the baseline, and as the spot moves, we will get two different lengths here. If the spot moves here, this is length L, and if the solvent moves up to this position, okay, then this is Y. Here, this is where the solvent has, right? So in that case, this factor will help us understand how far this can go, which is retardation factor, which is written as X by Y. Okay, so just keep this in mind, right? Next, partition chromatography is of a very similar kind, correct? So, which is paper chromatography as well. Not great details about it, just but note down the basic idea about how the mechanism works. Like what should be your stationary phase, which is liquid form of it, and then a mobile phase, which is liquid or a gas, which will help the spot to again go at different units. Here also we'll have same retardation factor, and based on that, you know what to do. Yeah. So guys, this is the basic idea you need to have from separation techniques. Got it? Next is about, quantitative analysis, qualitative analysis here. So that is qualitative analysis. One question is sure shot from this area, guys. Okay. So POC can give you two questions in paper. One would be from this, and one would be mainly from separation or other parts of it. But one question will definitely come from qualitative analysis. So learn it thoroughly. So here we are trying to detect all the elements: carbon, hydrogen, nitrogen, sulfur, chlorine, bromine, iodine, and phosphorus. Correct? So first, how do we observe whether there is any carbon present? See, first detection of carbon and hydrogen. So imagine like I have any hydrocarbon. If you heat it strongly with O2 in the presence of copper. Welcome to the world of Keystrong music. Bluetooth mode. Bluetooth device is ready to pair. Connected. Just keep it on mute better. Thank you. Right. Check. CXHY plus O2 in the presence of CuO. Right. So this will make that copper to get reduced and every part of carbon to get oxidized into carbon dioxide. So we take the amount of carbon dioxide I mean, whatever the gas that has been released, and pass it through calcium hydroxide. Clear? If it forms a milky precipitate, which means it is calcium carbonate. Okay, not precipitate, basically milky lime. So then it is going to be carbon dioxide present plus H2. But at the same time, every hydrogen that is present here will convert into H2O. H2O. So the same solution, if you pass it to copper sulfate solid anhydrous, which is white, plus H2O, correct? Then it will become CuSO4.5H2. Got it? Now this will be blue color. Now as per J mains, this is the most accepted structure. So remember that we will have 4 moles of OH2 here like this, right? With plus 2 charge on it, which is being attracted by one more water molecule and which is being attracted by SO4 2 minus. So one water molecule is only there for making hydrogen bonding. The rest of the 4 water molecules are getting coordinately bonded with copper. Okay. So this is detection of carbon and hydrogen. Next is detection of detection of nitrogen, sulfur, halogens, and phosphorus. Okay, if you are trying to detect these two, these it is called as Lessein's test. This is called Lessein's test. Correct. First, what we do, we convert into something called a sodium fusion extract. Yeah. So we are trying to heat it in a glass, fusion glass, which will completely get melted, when you heat it strongly, along with adding a lot of sodium. And if there is any if there is any carbon from hydrocarbon and there is a nitrogen present in it, then this will give a fusion mixture of NaCl liquid. Now, this type of an extract which you are getting, correct, is called as sodium extract, sodium fusion extract, sodium fusion extract. Now, this is to indicate that there is a presence of nitrogen. If there is a nitrogen present, then this could probably happen. Okay, so there is a nitrogen present, then this is a product that you can get. That is NaCN. If it is a sulfur present, right, then irrespective of carbon present or not, it will convert into Na2S liquid. This is also sodium fusion extract. In case if there is a halogen present, irrespective of carbon present or not, right, then it will become NaX liquid, right? And this X is chlorine, bromine, and iodine, correct? This is the first detection. Now notice for nitrogen, what are the tests which we use? 2NaCN, you add it with FeSO4, correct? First, it will become FeCN twice plus Na2SO4. And on excess amount of Fe, uh, excess amount of NaCN here, this will convert into Na4FeCN6. Correct? This is sodium hexacyano, 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 ferrate, ferrate 2. Then what you do here, you add some amount of concentrated H2SO4. For this, you can add some amount of H2SO here. So imagine if I take this compound here, whatever the Fe plus 2 present here with concentrated H2SO4 will convert that into small amount of Fe plus 3 and SO2 vapors. Now this Fe plus 3 is actually present in the form of FeO SO4 thrice. Now this amount, if you bring in contact with FeCN6, this complex. Okay, it is like this: you're taking another solution of FeSO4 here in another test tube with concentrated H2SO4, making it into oxidized form, then adding back to the original test tube here which contains this complex, and on adding that we will get it as Fe4 FeCN6 thrice. This is Prussian blue precipitate. Prussian blue precipitate. So this is a detection for identification of nitrogen present. Okay. Fails in which cases? Fails in the cases where you have if you have any diazonium salts here like N2 plus Cl minus, or if you have any diazo compounds here like this. So in these two cases, you will not see Lessing's test is observed for nitrogen. Clear? Apart of it, if you have hydrazine, let's say, hydrazine also does not give this test. Okay? Yeah. Hydrazine does not give this test. Why? Because there is no carbon in this case. Here, rest all the compounds will give the test any kind of nitrogen which is present in the form of amines or amides or cyanides or any form. They all will give you positive Lessing's test. Got it? So I'm hoping that all of you understood this part. Here, one important line which you need to understand from here is that suppose this was also asked in one of the exams, one of the sessions, that what if the nitrogen amount of nitrogen present is very less? Okay, if amount of amount of Na4FeCN6 is in less quantity. If this is less quantity means there is less amount of nitrogen. Okay, then you will see Prussian blue complex. Prussian blue complex will be in soluble form, and soluble form appears green in color. Soluble form and appears green in color. Right. So just keep this in mind for nitrogen. Nitrogen is only the most asked area, guys. So please be careful with the nitrogen part. What exactly it is. Right. Next one is about sulfur. Test for sulfur. In case of sulfur, we take Na2S, right? Because this is what has been formed as a sodium extract. Then we treat this with, lead acetate, by which we will get a black color PPT of PBS. Okay, plus 2 moles of CH3CONA. This is test number one. The other one, which is a main test, is that if you take Na2S, reacted this with Na2FeCN5NO, which is called as sodium nitroprusside. Sodium nitroprusside. Clear? So this sodium nitroprusside, after reacting, will become Na4FeCN5 times and NOS. Now remember, the oxidation state here of iron is +2 and here also it is +2. NO here is +1 oxidation state, NO is here is -1 oxidation state. So just keep that in mind. And the color here is violet. Okay. The other important test where nitrogen can be present here is when you have both. This is test for both N and S present, nitrogen and sulfur. If both of them are present, then sodium plus sulfur plus nitrogen plus carbon together will form NaSCN liquid. And if I take 3 moles of NaSCN, sodium thiocyanate plus FeCl3, then we will get this as FeSCN thrice, which is blood red coloration. This is blood red coloration plus 3 moles of NaCl. Okay. The coloration part can be expressed in many different complex form. That is SCN with plus 2 or FeSCN twice plus or FeSCN with H2O thrice and thrice like this. So in any of the form, it is always appearing to be red color. Okay, blood red color. Got it. Now, if excess sodium is added, excess sodium is added, then NaSCN will further react with sodium, convert into Na2S and NaCN separately. So you have to perform these two tests separately in that case. All right. Next one is test for halogens. Test for halogens. Now, Cl minus if you have there, which will come out as NaCl. NaCl plus AgNO3 will give us AgCl, white color PPT. And this white color PPT, if you add it in dilute ammonia, aqueous ammonium salt, which is dilute, then it will get dissolved to form ammonium, silver ammonium complex, soluble complex. This is soluble complex, okay? While if the same compound is been given this time with Br minus here, NaBr, so in that case, this will become AgBr precipitate. This was white, this was pale yellow, and this is pale yellow. And with ammonia, instead of dilute, now you should have concentrated. Only in concentrated it will get dissolved. Next, if you have NaI here, then this will become AgI, and even with concentrated ammonium aqueous solution, this will not get dissolved. So insoluble. So it will remain insoluble. So there is a detection for iodine. Okay. Usually, while performing for chlorides and bromides and iodide, we will just for the safe side, we will try to remove any cyanide or sulfur is present. So how do we do that here? Uh, right? What we do, we add these compounds with if by chance, note, if by chance NaCl plus Na2S are present in the solution, then we add small amount of concentrated HNO3 so that this will become NaNO3 and releases HCN vapors. Similarly, it can also release H2S vapors. So these two vapors will be gone so that there is no disturbance, for chlorides because AgCN and Ag2S are also precipitates, correct? So we don't want that precipitates to happen here. Next, another test for cyanide, for chlorides is a flame test, which is Beilstein test. Beilstein test is burning over the oxidizing flame of Bunsen burner. Correct. Now, if you take this organic substance and put it, if it indicates if green color or blue color is observed, this is the presence of halides. Presence of halides. Okay? That is one important note. Next one is layer test. Layer test. Layer test of these uh, especially done for bromides and chlorides here. That is, if you have Br minus plus Cl2, you will know it will convert into 2Cl minus plus Br2. Correct? And you do this in a layer of, chloroform or carbon tetrachloride, right? You can take CCl4 or CS2 or anything. Yeah. If it gives anything between yellow, orange, reddish to violet, sorry, not violet, brown, right? This coloring is the indication for bromine. Okay, depending upon what exactly solvent you are taking. But these options are given orange, red, red, brown. These kind of options are given. These are all for bromine. Clear? Next, if you have I minus 2, I minus plus Cl2, again in the presence of this solvent, it could be chloroform or any of that. So this will become 2Cl minus plus I2. And if it is I2, typically it will give violet color. So here it is, violet color in most of the solvent, violet color. This is a test for iodides. Next, it is test for phosphorus. Test for phosphorus. 2 phosphorus plus 5 moles of Na2O2. If by chance there is any phosphorus present in there, as you heat it with Na2O2, the entire phosphate will convert into Na3PO4 in peroxide, and this will remain Na2O. Got it? So 2 moles. Next, whatever the Na3PO4 which we got plus adding with nitric acid will convert that into H3PO4 and NaNO3. And this H3PO4 which we got, if you treat with 12 moles of ammonium, right? Ammonium molybdate, MOO4 plus 21 HNO3, 21 HNO3. So this would give us ammonium phosphate molybdate. This is ammonium phosphate molybdate plus 21 NH4 NO3 plus 12 moles of H2. I would strictly suggest mug up this entire balanced equation, guys. Anything could be asked from here because this is also going to be the quantitative analysis. So better learn it. Ammonium phospho molybdate. So learn what is the formula for ammonium phospho molybdate in this case. Got it? Done. This is a test for phosphorus. Next, quantitative analysis. If you check out the quantitative analysis here, we are trying to estimate the percentage of carbon, hydrogen, nitrogen, and so on. Okay. So for combustion, using combustion only, percentage carbon can be 12 by 44 into weight of carbon dioxide which you got divided by weight of organic compound into 100, while percentage hydrogen will be 2 by 18 into weight of H2O divided by weight of organic compound into 100. This is percentage hydrogen. Clear? Now, when it comes to nitrogen, in case of nitrogen, we have two methods. Okay, one is Dumas method. Sorry, Dumas method. The other one is Geldar's method. Correct. For Dumas method, what we do, we will pass the oxides of nitrogen with copper and convert everything into N2 gas. And this N2 gas is first collected in nitrometer, and from there percentage nitrogen is being found. So percentage nitrogen will be equal to 28, which is the molar mass, into volume collected at STP, volume of N2 at STP, divided by 22400 into weight of organic compound in grams, that into 100. So this is percentage nitrogen. Okay, clear? So this is about how much amount of percentage nitrogen we can get. So Dumas method, we can get any form of nitrogen, right? Whether it is azo or any kind of a form, we can easily get N2 gas from here. Sir, above NO is -1, then iron oxidation state of +2 is not matching. Above NO is not -1, beta, +1. NO we discussed here, see, +1. NO is +1, NOS is -1. Okay, Avira, clear? Fine. Chalo. Next, this is Dumas method and is valid for all of them. Next, Gelder's is the most important one. So learn this one carefully. Okay, Gelder's Gelder's method. For Gelder's method, we are supposed to use H2SO4. So here the logic is very simple. We add concentrated H2SO4 by which we are trying to convert every form of nitrogen into ammonia. Here, three important things you need to check. One is, what is the role of K2SO4? K2SO4 increases boiling point of H2SO4, increases boiling point of H2SO4, which is essential so that every nitrogen breaks into ammonia form. Next, CuSO4. What is the role of CuSO? It used as a catalyst to increase the rate. Yeah. Next, organic compound plus H2SO4 concentrated. As you add, it will convert into ammonium sulfate. The entire nitrogen part will convert into ammonium sulfate. Then we add NaOH on this so that ammonia gas can be evolved. Clear? So that it can form ammonia gas. And this, the amount of ammonia gas which is formed, sorry, the amount of NaOH which is present will be again treated off with H2SO4 so that rest of that will become Na2SO4 plus H2. In short, the equivalence of H2SO4 is being distributed for titration, that is equivalence of NaOH remaining, this is for remaining plus equivalence of ammonia formed. Always use this fundamental. Equivalence of H2SO4 will always be distributed into these two. So from here we can write percentage of nitrogen is equal to 14 by 1000 into volume of ammonia into normality, sorry, volume of H2SO4 into normality, that into weight of organic compound into 100. Yeah. Right. So this volume is only that volume which is used in the first case here. Sorry, in this case here. The, you know, how much amount of volume which we have used in the first equation. Got it? Here the important part is which fails Geldar's. Which one of this will fails Geldar's method? Correct. The group which will fail is azo. N double bond N is azo. Next, diazonium salt. It will fail for diazonium salt. Anything which is azo or azoxy, like that means if you have N with O group here like this. Next, nitraso, then nitro, here nitro. Then if you have nitrogen present as a ring form like this, even if there is no aromatic nature, then also this ring is not going to be given. Next, quinoline, which is benzene with this one. This will not give that quinoline part. So these type of groups, if you have, it will not give. Other than that, hydrazine, NH2, NH2. Even this will not give ammonia complete. Okay. So these are those compounds which does not give Jaldals. Rest of them will give Jaldals. Okay. So I guess all of you understood that. Next one is called Carrier's method. Carrier's method is a basically tube in which we will pass it, through fuming nitric acid. So through fuming nitric acid, we will get, various compounds and then pass it with silver nitrate, correct? With silver nitrate, if you pass it, I can get various precipitates. Percentage chlorine in that case will be 35.5, 143.5 into weight of AgCl by weight of organic compound into 100. Similarly, percentage bromine will be equal to 80 by 188 into weight of AgBr precipitate divided by weight of organic compound into 100. And percentage of iodine will be equal to 127 by 235 into weight of AgI divided by weight of organic compound into 100. Correct. Now, other than that, we can do it for sulfur also. So, percentage sulfur is equal to 32 by 233, which is the molar mass of barium sulfate. So, weight of barium sulfate divided by weight of organic compound into 100. Next, last one is percentage phosphorus. So, for percentage phosphorus, there are two ways we can make. But one is we can use this H3PO4 which we got with magnesium salt, so that we can get percentage phosphorus as 62 by 222 into weight of Mg2P2O7. This divided by weight of organic compound into 100, or percentage phosphorus, another formula which we can use is 31 by 1877 into weight of here ammonium. So NH4 thrice phosphate and then molybdate MOO3. So that divided by weight of organic compound into 100. So these are carriers methods by which we can, figure out what is the percentage of all other compounds. Got it? So I hope all of you got a gist of it, like what exactly we need to look out for. Okay. So from the POC's point of view, guys, these are the important areas that you need to remember. Got it? Now, getting into salt analysis. From salt analysis part, first check out cations. What are the cations you need to revise? Okay. The reactions as per NCRT, Pb2 plus, Cu2 plus, arsenic is important, guys. This is a part of NCRT. Then Al plus 3, then iron plus 3, correct? Manganese plus 2, nickel plus 2, right? Zinc plus 2, that means it is group 4, cobalt plus 2, then group 5, that is calcium plus 2, barium plus 2, then strontium plus 2, isn't it? After that, we have group 6, which is magnesium, and last group, which is ammonium, right? These are the cations we need to check out for. Clear? Then we have anions as well. Okay. So first let me go through cations and then we'll come to anions. Got it? So in case of cations, what are the cations we need to look out for? I mean, as per this cation test, let us see. First basic indication we need to have is cation based on their colors. Correct? These are the metal ion colors. When it is been heated on Bunsen burner. Correct? So first heating and color. Correct? So if it is Fe plus 2 or Fe plus 3, typically it is light green to brown. If you see anything light green to brown, these are the compounds. Next, Cu2 plus is always blue color. Nickel 2 plus is, green color. And cobalt 2 plus is going to have a lot of colors, but typically again blue color. Manganese 2 plus is light pink color. Okay. These are characteristic colors of metals. Okay. Next, if you have different coloring on heating, clear? So in cold and hot, especially when it comes to oxidizing flame, okay. So in oxidizing flame, copper 2 plus, usually it is blue color, right? When it is hot, sorry, when it is cold, and if it is hot, it is going to be white color. Fe plus 2, it is green color, and dirty whitish to yellow. Okay. Next, Zn2 plus, it is white color and yellow color. Mostly if it exists in the form of oxides. Okay. Next, cobalt plus 2, it is pink color and blue color. Right. So I'm sure you remember the borax bead test. This one is borax bead for these cations. Okay. Now, if you notice Na4B2O7.10H2, which is borax, on heating will swell into Na2 uh, B4O7. It's also Na2 B4 plus 10H2. And this will further divide into beads, which is NaBO2 plus B2O3 and hydrogen. Now, suppose if I take copper sulfate or copper 2 plus, and if I heat it with the oxidizing flame, right? Oxidizing flame is non-luminous. Then first it will become a cupric metaborate like this. This is cupric metaborate plus SO3, right? So this is that blue-green color on oxidizing flame, okay? And if you take this copper sulfate, I mean CuBO2 twice plus more of NaBO2, more borate in the presence of carbon. Carbon soot will be present when you have reducing flame. So in reducing flame, it will become CuBO2 plus Na2B4O7 plus carbon monoxide gas. So this will get reduced into this form. First reduction. This is first reduction. If you keep further, a further reaction here. So this same CuBO2 will further react with 4 moles of NaBO2 plus 2 moles of carbon to give 2 moles of copper. Okay, sorry, here also I need to take 2 moles plus 2 moles of Na2B4O7 plus 2 moles of CO. Eventually, what you get is copper. Most of the cases, this is what we need to do. I gave you the colors already for borax bead test. What is that with copper, nickel, manganese, and iron, cobalt, and chromium. So I'm sure you remember these six, correct? So next one is charcoal cavity test. Charcoal cavity test. In case of charcoal cavity test, here basically compounds which were not able to give that color, we usually do that. First, we can do this for copper sulfate also. Copper sulfate, if you react with Na2CO3, basically you are adding Na2CO3 in that cavity and heating it strongly so that it will become CuCO4 and CO3 and Na2SO4. And CuCO3 that on strong heating will become CuO and CO2. And this CuO plus carbon and heating will give you copper, which is red color plus carbon monoxide. That is how we can check out the color. Same way, zinc can also be observed in a similar way. Clear? So ZnSO4 plus Na2CO3 will become ZnCO3 plus Na2SO4, and ZnCO3 on also on heating will give you ZnO plus CO2. Now ZnO has two properties here, beta. ZnO, correct? It will be in equilibrium with another ZnO. Clear? If it is heated, on heating this side, it will be yellow. And when it is cooled, when it is cooling, right? Sorry, above all, right? Heating this side, okay? Temperature decreasing, that is cooling this side. On cooling, it will become white. So it is a white color powder on cold, and on heating, it will be yellow. Okay. This is charcoal cavity test. Then it is cobalt nitrate test. Cobalt nitrate test. In cobalt nitrate test, basically we are trying to make a complex with cobalt so that it can impart color. So cobalt nitrate on strong heating will convert into cobalt oxide plus NO2 plus O2. Okay. Now this cobalt oxide, if it is with zinc oxide, it will give you COO.ZnO, which is, green color. Yeah. So this is green color formation. Okay. If it is with MgO, then it is COO.MgO, which is pink color. If it is Al2O3, it will be CaO.Al2O3, which is Ternard blue color. Mainly these are used for zinc, magnesium, and aluminum. So just keep that in mind. Okay. Next, for analyzing the cations, right? First, we need to make original solution. Make original solution OS. Original solution. Original solution is basically made by adding dilute HCl. If it is not dissolving, add concentrated HCl. If still it is not dissolving, you heat it till the time everything will become a solution. As long as we get a solution, colorless solution, then we do that. That is called the original solution. So imagine I have original solution. First, zero, zero group. So zero group is specifically for ammonium salt. So directly you distribute one of the, you make one test tube only for checking ammonium. Yeah. In case if you have ammonium ion, correct? Ammonium ion. So with HCl, when you have, right? So this will definitely be in the form of ammonium chloride. So this will be observed as ammonium chloride. Now, what you do, you pass this ammonium with some base to Nessler's reagent. That is 2 moles of K2HgI4 plus ammonium chloride in the presence of 3 moles of KOH. In that case, what would happen here is we'll get this as HgO dot HgNH2I. Instead of ammonium chloride in NCERT, it is given as ammonia, where you notice that this ammonium chloride has been initially already added to some amount of KOH to get this ammonia to release, and from there, this ammonia has been added to the Nessler's reagent. So this is the compound form. Correct. In this case, we have oxygen and NH2 are at the bridge positions with two mercuries this way. This is the structure which you have with plus and iodine minus. And this will be a brown precipitate, a brown PPT, plus 7 moles of Ki plus 2H2O. So this is the overall reaction, guys. So remember, this is basic mercury to amido iodine. Alright, amido iodine. Right. One group table is very, very important, guys. Okay. What is the group table? What is cation? What is a group reagent? Okay. So check out, this is group number and cations. What are the cations you are analyzing? And what are the group reagent that you are adding? So first one is 0. So 0 is NH4 plus which you are analyzing. There is no reagent here. Next, group 1. Pb plus 2, correct? Others are Ag plus and Hg, but this is not in the syllabus. Pb plus 2, Ag plus and Hg2 2 plus. Only this part is in syllabus. Pb2 plus is in syllabus. So here we use dilute HCl as a group reagent. Group 2. Group 2 we have lot of them, but again here Pb2 plus also again used, copper 2 plus and As plus 3. There are many more, but this is the one which you will be using in NCRT. H2S plus dilute HCl. Next, group 3, analyze only Al plus 3 and Fe plus 3. And the reagent is NH4OH plus NH4Cl. Got it? Similarly, if you notice group 4 we have cobalt 2 plus, nickel 2 plus, Mg2 plus, and not Mg, sorry, Mn2 plus and Zn2 plus. And here we have H2S plus NH4OH. Group 5, we have barium 2 plus, strontium 2 plus, calcium 2 plus, and this is in the presence of carbonate, ammonium bicarbonate with NH4OH. And group 6, we have Mg2 plus, again none. So these are the reagents we need to analyze this. All right. So for last year, mainly they have asked lead compounds. So see what are the lead reactions here. Pb2 plus reactions. So first PbCl2, correct? If it is a hot solution, plus 2 moles of Ki. Hot solution is a soluble form, a white PPT, which is in a soluble form. When you react it with 2 Ki, it will become PbI2, a yellow color PPT. A yellow color PPT. Here, so remember PbCl2, PbBr2 are generally white, okay, while PbI2 is yellow. Just keep this in mind. Next, if you react the same thing with K2CrO4 or Na2CrO4, which is yellow color solution, will convert into a yellow color PPT. Lead chromate as a yellow color PPT, right? And this lead chromate, if you add it with 4 moles of NaOH, okay, so then this will become Na2PbOH4, a soluble colorless solution. Okay. Now this has been asked many times. Last year it was asked in 2 sessions. Okay. What is that complex which is formed on adding with NaOH? Okay. So learn that what is the complex formed here, right? Plus you'll have yellow color solution of Na2CrO4. Okay. Next. If you treat this with H2SO4, you will get PbSO4, a white color PPT. This is a white color PPT here. And if this white color PPT has been added with ammonium acetate salt, 4 moles of that, again you will get a complex formation just like above. Ammonium PbCH3CO4 times soluble complex, correct? This one also was asked in one of the sessions. So you could imagine the importance here. Okay. This type of on excess, what is a complex form? This type of questions you should learn more often. Okay. This was asked in 2 sessions, guys. So please be aware of it, how to make it. Yeah. Next. In the case of second group, which is again Pb2 plus is being used, but this time we have a precipitate of PbS. So in case if you have PbS as a precipitate here, then what are the reactions you should see? So first, PbS plus 8 moles of HNO3. So that will convert into 3 moles of PbNO3 twice, which is soluble form, plus 2 moles of NO gas, plus 4 moles of H2O plus 3 moles of colloidal sulfur. This is the colloidal sulfur which you will get. And PbNO3, as you treat with H2SO4, it will convert into PbSO4 white color PPT. Here, this is what we need to check. And like I said, the same logic here. This, if you add it with ammonium, excess of ammonium acetate, correct? So that will convert into ammonium. Sorry, just I'll pass on to the arrow directly. From here, again, you will get this part, right? This is about PBS. Okay. Now, by chance, if you have chromate or iodide, you'll get yellow color PPTs. Next, check out for copper 2 plus. Copper 2 plus, what do we need to learn? See, copper 2 plus is also a sulfide form. This sulfide form, same reaction, 8 moles of HNO3. It is asked as 3 moles of copper nitrate plus 2 moles of NO plus 3 moles of colloidal sulfur plus 4 moles of H2. Hey, this was asked in one session as a balanced equation. Okay. Actually, they have given the reaction. They put it, they asked to balance the reaction. Correct. So you can see how different ways it can be asked. So learn this reaction, which is very similar to all the plus two ions. Okay. Clear. Now, whatever the colloidal sulfur which we got, if you treat this with HNO3 further, it will convert into H2SO4 plus NO gas. So, suppose if you have a copper sulfate solution, this was the original solution. Then you add it with ammonia. On adding with ammonia, you will get first copper hydroxide and copper sulfate. This will be a blue color precipitate. This will be a blue color precipitate plus 2 NH4 plus. But this one, if you add it with excess amount of ammonia, if you are adding, correct, then 8 moles of excess ammonia, then you will get 2 moles of copper NH3 4 times with sulfate. This is deep blue solution known as Switzer's solution. This is copper 2 plus reaction. Okay. Continuing further, if this deep blue red solution here, if you pass it with acetic acid, 4 moles of CH3COOH, it will again convert back into copper sulfate, solution, copper sulfate solution, and 4 moles of CH3COONH4. So now this solution will become light blue. So this solution will become light blue. Got it? What we do from this copper sulfate, the light blue solution, if you pass it through uh, ferrocyanide, potassium ferrocyanide, it will give us Cu2FeCN6, Cu2FeCN6, which is chocolate brown precipitate plus K2SO4. So you can see two important conformations for copper. One is this deep blue coloration, and following that chocolate brown precipitate formation. So if you are able to do that, then this is for copper 2 plus. Next is for arsenic. A is plus 3. Arsenic is in plus 3 form. Now what we do in case of arsenic, AS2, S3 is there. We add with yellow ammonium sulfate, that is NH4 twice and S2. This is called YAS, yellow ammonium sulfate. With yellow ammonium sulfate, you'll get 2 moles of NH4 thrice and AS4 plus sulfur, correct? And these 2 moles of NH4 thrice ASS4, which is a soluble form here, plus 6 moles of HCl will give us AS2S5 plus 3 moles of H2S plus 6 moles of ammonium chloride. And lastly, this is last reaction has been asked in one of the sessions. This one, this reaction has been asked. That is plus 10 moles of HNO3 plus 4 moles of H2O, 4 moles of H2O would give us 6 moles of H3ASO4, which is arsenic acid, soluble acid, plus 10 moles of NO, plus 15 moles of sulfur, colloidal sulfur. Okay, and this is the conformation reaction of the same with 12 moles of ammonium molybdate will give us, ammonium molybdate with 21 HNO3, correct? That would give us ammonium arsenic molybdate, MO3 O10 4 times. So this is ammonium arsenic molybdate, which is yellow PPT. This is a conformation for uh, arsenic. Clear? So this is an area which you require a thorough practice because this is very difficult to learn. And remember, keep it this as a star mark that before your session, if tomorrow is your session, just day before that you will write and learn. Okay, especially for arsenic, everybody. So one day before your exam, please make sure you write and learn what exactly are the reactions for arsenic. Okay, prepare for the worst. Okay, right. Next one is aluminium, Al plus 3. Al plus 3, whatever the chloride which has been formed, if you treat with 3 moles of NaOH, it will become AlOH thrice plus 3 moles of NaCl. Now this is in white gelatinous precipitate, white gel precipitate plus NaOH excess if you add, it will become a soluble form as NaAlO2, which is sodium meta aluminate. And sodium meta aluminate is a soluble salt form. Or you can also write this as NaAlOH4. So either ways you write it is the same test. Clear? Right. Correct. Next, check out the second test here. See, if aluminium, okay, if you notice the aluminium form here, that is AlCl3, if you're adding with blue litmus paper, if you notice litmus paper, blue litmus form, if it is added, right, in the presence of NH4OH here, and NH4OH is to be added drop by drop, then this will become an alkaline, it will become an alkaline aluminium hydroxide. So it will have more alkaline nature. Okay. And while this is getting precipitated here, it will this will blue color, blue color and give a complementary color. And that complementary color will be, red coloration. Red coloration. This is the complementary color. Okay. And this test is called Lake test. This is called Lake test for aluminum. Okay. Next one for Fe plus Fe plus 2 or Fe plus 3. Sorry, Fe plus 3, not for Fe plus 2. For Fe plus 3, the reaction is simple. Whatever the hydroxide which is formed as a precipitate, usually hydroxide in this case, which is formed is brown color precipitate, which when you add it with HCl becomes again colorless, forming FeCl3 plus H2O. Now, this FeCl3 colorless solution, when you react with 3 moles of K4FeCN6, correct? So you can see it is a plus 2 plus 3 combination. So which will form Fe4 and FeCN6 thrice. Now this is Prussian blue PPT plus 12 moles of KCl. Correct? Now, if this one is added in excess, if this one K4 FeCN6, correct, is added in excess, then it will appear like this K4 KFe FeCN6, right? This is called soluble Prussian blue color. Soluble Prussian blue color. So remember if it is excess or not. Okay. If you have Fe plus 3 and react with thiocyanate, we learned it already that it will form FeSCN thrice, which is red coloration. These two are the important confirmatory tests. Alright. Next, zinc. Zn2 plus is being precipitated as zinc sulfide, which is white color. Zinc sulfide is white color. And if you add it to acids, it will get dissolved to form ZnCl2 plus H2S vapors. And this dissolved Zn2Cl2, which is colorless, if you react with NaOH, first it will become a white PPT. This will become a white PPT. And this white PPT, when you add it with excess of NaOH, will convert into Na2ZnO2, which is soluble form. This is soluble form. Then the other reaction is ZnCl2. If you react with K4FeCN6, K4FeCN6 will convert into Zn2FeCN6, and this is also a white PPT. This is a white PPT plus 4 moles of KCl. Then manganese, Mn plus 2, right? These areas haven't been asked very well touched with J mains. I'm just writing in case only, okay? So MnCl2 plus H2S, okay? And here MnCl2, interestingly, just like uh, zinc, it will also forms a white PPT. This is also a white PPT, correct? And this MnOH twice, if you keep it in air for longer time, so this will get oxidized to form this plus 3 group here. I mean plus 4 group here. So this is brown color PPT. Brown color PPT. That's it. Next, nickel plus 2. Which I got for nickel plus 2. Whatever the sulfide which has been formed, which is black color, that when you treat with HNO3 plus 6 moles of HCl, this is called aqua regia. So we are not directly, we are not only reacting with HNO3, we are using with an aqua regia form. Then you will get 3 moles of NiCl2, which is green color, plus 2 moles of NO, plus 3 moles of sulfur, plus 4 moles of H2. Correct? This is a soluble green color form. And this, when you add it with NiCl2, if you add it with NH4OH and DMG, okay, 2 moles of DMG. So if you recall, DMG structure is very important, guys. CC, double bond N, double bond N, methyl and methyl. Similarly, CC, double bond N, double bond N, methyl and methyl. Nickel is at the center. These 4 nitrogens are connected, correct? And here it will be O minus, which is, sorry, which is O minus, which is connected to hydrogen, which is connected to oxygen here like this. So this is a hydrogen bonding which you will get. Similarly, here we will get O and H, which is connected with oxygen like this with O minus, right? So you can see a 5-membered ring, 5-membered ring, and a 6-membered chelation and a 6-membered chelation via hydrogen bonding. So that makes this nickel DMG very stable complex. So it is a highly stable complex which is as nickel DMg twice. And the color is cherry red precipitate. Okay. Brilliant red or cherry red, the same. Right. Clear beta? Next, cobalt plus 2. If you see cobalt plus 2, cobalt sulfide plus again we react with aqua regia. This is aqua regia. So then you will get COCl2 plus NaOCl plus sulfur plus 2 moles of H2. Okay. Just a minute. Sorry, check out. Next, COCl2 plus what we do is we add a nitrite KNO2 plus 2 moles of CH3COOH, which will give us K3CONO36, correct, plus 2 moles of KCl plus 2 moles of CH3COOK plus NO. So basically one of the nitrogen will get reduced, cobalt will get oxidized, and this will become potassium hexanitro-cobalt, which is yellow PPT. This is yellow PPT. This was also asked in one of the sessions, like what is a PPT, which is formed for formation of cobalt plus 2. Okay. Next, in case of barium 2 plus. In case of barium 2 plus, simply first we get a barium carbonate during the test, which will react with acetic acid to convert into a soluble barium acetate. This is a soluble salt, correct? And this barium acetate, when you treat with K2CrO4, will convert into BaCrO4, which is yellow PPT. This is a conformation for barium. Clear? Now, barium complexes, I mean, barium salts usually glow with green color in the flame. That you know that. That is a test we can do for this. Strontium 2 plus. Strontium 2 plus, we'll get SrCO3 plus 2 moles of CH3COOH. We'll get soluble acetate here, CH3COO twice, and Sr. And that, if you treat with ammonium sulfate, NH4 twice, SO4, then we'll get SrSO4, which is white PPT of sulfate. Got it? The flame test here will give you brick red color, sorry, crimson red color. For strontium, it is crimson red. Calcium 2 plus, or calcium 2 plus calcium carbonate plus 2 moles of CH3COOH is giving CH3CO twice Ca plus H2O plus CO2. Now this, when you add it with ammonium oxalate, ammonium oxalate, that will give you white color PPT of CaC2O4. White color PPT, that is a confirmation. And in flame test, it will glow as a brick red color. Got it? And lastly, magnesium 2 plus. Magnesium 2 plus, you know, there is only one test, magnesium 2 plus salts directly added with sodium hydrogen phosphate. That will give you MgNH4, right? MgNH4 PO4. All right. Okay. This we have to add in the presence of ammonium. Okay. Then plus NH4OH plus 2 moles of Na plus H2O will be formed. And this is a white PPT. white PPT. Got it? These are the confirmatory tests for, cations, guys. So take out some time, go through the cationic test once. Okay. Now let us see what are the anions we need to learn. Okay. What are the important anions we need to learn out of that? The first, uh, for carbonate and all, these are easy ones. So we'll quickly go through that first. See, first is carbonate, CO3 2 minus. Carbonate can be easily identified even with dilute solutions. So if you add dilute HCl, you'll get carbon dioxide gas easy. Now what you do, if there is any form of carbonate, CO3 2 minus, add it with dilute H plus, so it will convert into H2O and CO2, right? This CO2 is to be passed with calcium carbonate, sorry, calcium hydroxide to convert into calcium carbonate PPT, which is white color PPT. Okay. And if you add excess of carbon dioxide, this will become a soluble complex, a soluble salt, which is bicarbonate, right? This is a conformation for carbonate. Next, sulfide, S2 minus. For S2 minus, if you have a salt like Na2S, you add dilute H plus. Dilute H plus could be H2SO4 or HCl. NCRT given as H2SO4, so use that as H2SO4 only. Then we will get this as Na2SO4 plus H2S. Got it? H2S vapors are rotten egg smell. This is rotten egg smell. And this rotten egg smell, if you add it with CH3COO twice Pb, lead acetate, we will get PBS, a black color PPT. Black color PPT here. Correct? More importantly, the confirmatory test, which we already done in Lassane's test. This is the same thing we did it in Lassane's test. Is Na2FeCN5NO. If you recall, this is the uh, sodium nitroprusside form, which will convert into Na4FeCN5NOS. This is the violet color, violet or purple color complex formation. Next. If you have SO3 2 minus sulfide here, in case of sulfide, again we add dilute dilute H2SO4. On dilute H2SO4, we will get this as SO2 gas plus Na2SO4. Now, what we do is K2Cr2O7, when you treat with H2SO, I mean SO3, SO2 in the presence of H2SO4, it will convert into a green color solution of sulfate. This is green solution. Okay, this is a green color solution. That is a confirmation for the following. Okay. The other reaction is SO3 2 minus salts. If you directly react with barium chloride or something, this will become a white PPT of BaSO3. Okay, barium sulfide, white PPTs. Got it? In fact, if you add this to concentrated H2SO4, right, this will again become barium sulfate, which is also white PPT, releasing some amount of SO2 gas here. Correct? This is one way of looking at it. Same way we can do that KMNO4 with KMNO4 reaction also with SO2. Okay. Next, NO2 minus. Okay. NO2 minus also, if you add it with dilute H2SO4, okay, first it will become HNO2 vapors with Na2SO4. This HNO2 vapors are unstable. HNO2 in fact is unstable form. It will undergo disproportionation to HNO3 and 2 moles of NO gas plus H2O. Okay. This is an important reaction even from inorganics point of view, guys. So remember this reaction. But Now 2 moles of NO, because you will expose this to air, aerial oxidation will take place and convert into a brown color gas. Okay, brown gas. And that brown gas is NO2. Got it? Which means if I take any nitrite ion, if you add it with an acetic acid, first I'll get HNO2 plus CH3CO minus. And this HNO2, if you treat with Ki and CH3COOH excess, you will get this as 2 moles of CH3COOK plus 2 moles of H2O plus NO gas plus I2. So I minus is getting oxidized to I2 and HNO2 is getting reduced to NO. And whatever the I2 which has come, if it is in contact with starch, it will convert into blue color complex. This is one confirmatory for NO2 minus. Okay. Another confirmatory, this somehow it was very focusedly asked on 2022. You will see some questions in 2022 where first you are making HNO2 here, and this HNO2 is being treated with you know sulfonalic acid here, SO3H with NH2. This is sulfonalic acid, correct? And this plus CH3CO minus. So because of the CH3CO minus, it will be acid base reaction here. Now this together will form something like N double bond N, N double bond N with N double bond N with plus charge here, correct? Sorry, triple bond N with plus charge here and CH3 COO minus. And here we'll have SO3H plus 2 moles of H2O. This is the compound which is formed. Okay. Once you get this, this is a diazo compound, isn't it? So this diazo compound, if you treat with, naphthyl amine, right? Naphthyl amine is this one. This one is naphthyl amine, which is at alpha naphthyl amine, alpha naphthyl amine, treated with this disonium salt here, which is N2 plus SO3H plus CH3CO minus. This will have an attachment on para position. So N double bond N with benzene and SO3H. And this is red color diazo compound, red azo dye. Clear? This is the test for NO2 minus. Okay. Next. If you see test for acetate CH3CO minus, I'll come to the brown ring test, along with NO3 minus. First, let me finish CH3CO minus. So CH3CO minus also, if you treat with dilute H2SO4, correct? So that will convert into CH3COOH, which will be a vinegar-like vapors. Okay, so this is vinegar vapors, and that when you treat with ethanol, it will convert into a fruity smelling liquid, which is fruit smell, which are ethers, sorry, which are esters, okay. This one is a very important reaction. Last year also asked many times. This acetate ion, when you treat with Fe plus 3 plus 2 moles of H2O, it will give FeOH twice and CH3CO 6 times. This is the complex we are talking about. Plus 2 moles of H plus. This complex is actually, a red color solution. Red color solution. So this is not a PPT, but this solution, right? This solution, if you treat with 4 moles of H2O, correct? So that will convert into 3 moles of FeOH twice and CH3COO, all right, plus 3 moles of CH3COOH. So this will be brown red PPT. Guys, these two reactions are very, very important. They have been asking straight away from this, lab book. From the lab book, they are straight away asking this, whether it is a colored form, whether it is a precipitate form to this extent. So learn it. Okay. So next confirmatory test this time is for chlorides and bromides and iodides. Cl minus. For Cl minus, right? We need to add a concentrated H2SO4. So adding concentrated H2SO4, we will get this as NaHSO4 plus HCl vapors. Correct. So HCl plus ammonia will give you white fumes, NH4Cl, which is white color fumes, like cloud like fumes you will get. Okay. Next, we can also use MnO2 to oxidize this. So if there is any chloride salt in acidic medium, it will get oxidized to form Cl2 and MnSO4. And this Cl2 is the gas which is evolved, which is pungent gold yellow smell. The other important confirmation is AgNO3, which we have done the same thing in Lassigne's test. So which is formation of AgCl, white color PPT, and that in the presence of ammonium hydroxide will form a complex NH3 twice plus Cl minus, which is soluble complex. Okay. So this is a confirmatory test for chlorides. One of the important confirmatory tests for chloride is a chromyl chloride test, which is a very, very important test for JEE mains. See, this should be a ionic chloride like NaCl. NaCl, when you treat with K2Cr2O7 plus 6 moles of H2SO4, will convert into 2 moles of KHSO4 plus 2 moles of CrO2Cl2 plus 4 moles of NaHSO4 plus 3 moles of H2. Now this is chromyl chloride test. I mean chromyl chloride vapors, which is red color vapors. So this red color vapors CrO2Cl2 plus 4 moles of NaOH, that will convert into Na2CrO4 plus 2 moles of NaCl plus 2 moles of H2. And this is yellow color solution. And this yellow color solution, if you pass it through lead acetate solution, it will convert into PbCrO4, which is yellow color PPT. Up to this yellow color formation, you need to do this. Got it? Got it. See, other form is if you take this CrO4 minus here and add 10 percentage of peroxide H2O2 and gently shake this out, then we will get it into CrO5, which is blue coloration of this complex, okay, chromium pentoxide. And this is about chloride. What is about bromide? Br minus. 2 moles of NaBr plus 2 moles of H2SO4 will give us Br2 plus SO2 plus Na2SO4. Now, Br2 is the direct form which you will get. This bromine gas which is released is actually reddish brown, red brown vapors. Okay, that is a confirmatory form. First test for that. Then you react with MnO2 also, same logic with H plus, you will get Br2 plus MnSO4. And this is also the same thing. Now, layer test, which we have done it already, NaBr plus Cl2, it will convert into 2 moles of NaCl plus Br2. So, in the presence of organic layer, okay. So, depending upon which particular layer you are taking, we can get different colors here. So, usually, like I said, orange, red, brown. So, anywhere in this range, whatever you have, it is bromine gas. Next, I mean bromine liquid. Okay. Next is with iodide. For iodide also, if you notice, 2 moles of NaI plus concentrated H2SO4. That would give us Na2SO4 plus SO2 plus I2. I2 starch is one reaction which you can easily make out. Along with that, we can have reaction with MnO2, same reaction, and then layer test. 2NaI plus Cl2 is giving NaCl plus I2. This is typically violet coloration in organic layer. Organic layer. This is the formation for iodide. Notice it for NO3 minus. This one is the important part. Last one, which is important part here. So NO3 minus plus H2SO4. That would first give out NaHSO4 and HNO3. Notice it carefully. So we have to heat it a bit. For this reaction, we need to heat it a bit. And this HNO3 will get decomposed into 4 moles of NO2 plus O2 plus 2 moles of H2O. Again, this reaction is also important from the inorganics point of view. So we will get this as NO2, which is brown color gas here. Next, once you get this form here, this NO2 fumes are being formed. This is a confirmatory test which you will have. Another one is that NaNO3, if you have nitrate, we have in acidic medium in the presence of copper. If you take it in the presence of copper, it will convert into a blue color solution of copper sulfate aqueous plus Na2SO4 plus 2 moles of NO, 2 moles of NO gas. And again, this NO gas, if you keep it in air for some time, it will convert into uh, brown color vapors. Got it? See, when it comes to brown ring test, check out brown ring test. For brown ring test here, first we got HNO3, isn't it? From HNO3, we treat this HNO3, 2 moles of this, with 6 moles of FeSO4. That means we slightly add drop by drop of ferrous sulfate from the side walls. Then we already have H2SO4 in it. As it reacts, it will get oxidized basically. So to from Fe plus 2, it will get oxidized to Fe plus 3, and we will get NO gas here, correct? And whatever the FeSO4 which is present with that NO will convert into FeO, H2O5 and SO4, correct? This is that brown ring vapor. So it will be forming this brown ring vapor. Okay. Now, in the brown ring, since we are in the brown ring form, if it is NO2 minus with dilute H2SO4, we have already noticed that it will form HNO2, right? And HNO2 will not stay stable. It will undergo disproportionation to give NO. And directly you react this FeSO4 dilute with this one from the walls of it. It will convert into this FeNO H2O5 SO4. So both will give brown ring test in a different condition. NO2 minus will give in dilute H2SO4, while NO3 minus will give in concentrated H2SO4. All right. Next, oxalate and oxalate form is with KMNO4, that I'm sure you are aware of. sulfate, oxalate, phosphate. Phosphate, we have seen it already, correct? What kind of a precipitate we will get? Okay. What is the oxidation state of iron in brown ring? Okay. For brown ring, please take it as +1 as much as mains is concerned. No change. Okay. Here, NO is neutral here, but it is 3 electron donor, because of which iron already has 1 electron. So that's why iron will have +1 oxidation state. So I guess all of you understood this part. Yeah. Now, these are the areas you got to revise it, everybody, by writing. Okay. Yes. Take out some time. First, read out all the separation techniques and important areas of chromatography. What was asked in last year, specifically focus on 24 and 23. What is the type of question that was asked? And then check out Lassen's test. Geldals is a very important area. Then cobalt nitrate test. Then borax bead test, their colors. Right. After that, what are all the cations? And their confirmatory test, as well as anions and their confirmatory test. Clear, everyone? So I'm hoping that this should help you out. Okay.